Somewhere inside a laboratory in Nanjing, a wireless signal just carried enough data through open air to pull down every single film in the Netflix catalog in about the time it takes you to tie a shoelace. No cable, no fiber, no wire of any kind. Just air. The same air sitting in the room around you right now, moving 206 gigabits every second. In this video, we are going to break down exactly what China built, why that one number made engineers in Seoul, Tokyo, Washington, and Brussels start writing enormous checks within months, and what all of it means for the phone sitting in your pocket. To give you a sense of scale, the 5G connection on your phone, on a good day, in a good spot, gives you somewhere around 300 megabits per second. What that team in China measured is roughly 100 times that. And the part that genuinely rattled people is not even the speed. It is the chip they built to make it possible, because that chip is smaller than your thumbnail. And it does something no other piece of silicon on Earth can currently do. I am going to explain exactly what that chip does and why it matters. But before that, you need to understand the problem it was built to solve. Because that problem is quietly shaping your life every single day, whether you notice it or not. Your phone runs on wireless. So does your car. So does the equipment in the hospital your doctor works in, and the factory that produces the medication in your bathroom cabinet. All of it depends on signals moving through the air, and here is what almost nobody stops to think about. Every single time the world has jumped from one generation of wireless to the next, it has not simply made phones a bit quicker. It has rearranged where money and influence sit on the map. Look at what happened when we went from 3G to 4G. That one jump gave us Uber. It gave us Instagram. It built an app economy worth $400 billion that had not existed the year before. Nobody planned it. It happened because faster wireless suddenly made a whole category of things possible that had been impossible 12 months earlier. 5G was supposed to do exactly the same thing for self-driving cars, for remote surgery, for factories that coordinate themselves. It did not. And the reason it did not is precisely why what China just pulled off matters so much to everybody else. If you want to understand what is actually happening here and why it could decide who controls the technology you depend on, hit that like button and subscribe right now, because this story is moving quickly and most people are going to miss it entirely. Let me explain the fundamental problem with wireless in a way that will stick with you, because once you hear it, everything else in this video clicks into place. A wireless signal is nothing more than a wave traveling through the air. Some waves vibrate slowly, some vibrate incredibly fast. That single difference decides everything a signal can and cannot do. Slow waves are tough. They travel enormous distances. They pass through walls. They keep working in heavy rain. That is why AM radio used to reach a kitchen 100 miles from the transmitter. Your grandfather could listen to a ball game being played 3 states away and the sound arrived scratchy and thin, but it arrived. The catch is that slow waves cannot carry very much information. Picture yourself shouting across a football pitch. Your voice makes it all the way to the far end, but you are only ever getting a handful of words across. Fast waves are the exact opposite. They can carry staggering amounts of data because every vibration is another opportunity to hold a piece of information, and they vibrate millions of times more often. The trouble is that they are delicate. A wall stops them. Rain scatters them. They fade out after a very short distance. Picture yourself whispering a long, detailed secret. You can say an enormous amount, but the other person has to be standing right beside you or they hear nothing at all. Reach or speed, choose one. That trade-off has been the governing rule of wireless communication since the very first signal was ever pushed through the air. And it is the single reason 5G has been such a letdown for most people. The version of 5G they put in the adverts used those very fast waves. On paper, the numbers looked spectacular. In practice, those signals struggled to cross 2 city blocks. A tree could block them. A window could weaken them. Your own hand wrapped around the phone could interfere with the connection. Which is why the 5G your phone is connected to at this moment is mostly running on the same kind of waves 4G used, tidied up a little. Real-world speeds land somewhere between 200 and 500 megabits per second. Faster than a decade ago, absolutely. Nowhere near what was promised. Put it another way, You are paying for 5G. The little symbol in the corner of your screen says 5G. What you are actually receiving most of the time is a slightly improved 4G. The label changed. The experience barely moved. And that is not because the technology is broken. It is because the fast version only works if you are standing more or less underneath the antenna with nothing in between. Which is not how a single human being on Earth actually uses a phone. And this was never really about downloading films quicker. 5G was meant to be the network where self-driving cars talk to each other in real time. Where a surgeon in one city guides a robotic arm in another. Where an entire factory floor becomes one wirelessly coordinated machine. Those things need tens of gigabits per second, and reaction times measured in slivers of a millisecond. The 5G you're using is not remotely close. Here is where the scale of the problem really lands. By the end of 2025, China alone had put up 4.5 million 5G towers. That is more than every other country on the planet combined. More than 1 billion people in China were connected to it. And even with all of that concrete and steel in the ground, the speeds ordinary people experienced were still a fraction of what had been advertised. The infrastructure was there. The physics was still standing in the way. That is the moment Chinese researchers stopped trying to squeeze a little more out of 5G and asked a completely different question. What if you skipped past every one of these limits and went straight for the fastest waves that exist? Waves so fast that nobody in the history of communication has ever managed to use them for anything practical. Those waves live in a slice of the spectrum called terahertz. Hold on to that word because it is the thread running through everything from here to the end of this video. Now, why were terahertz waves written off as unusable? Once you understand this part, the breakthrough hits completely differently. Terahertz waves can carry a genuinely absurd amount of data, far beyond anything 5G touches. But they are unbelievably fragile. Moisture in the air kills them. Walls stop them dead. Humidity on a warm afternoon is enough to weaken the signal noticeably. For decades, scientists referred to this stretch of frequencies as the terahertz gap, because the potential sitting inside it was enormous and completely out of reach. It was like owning a car capable of 1,000 miles an hour that disintegrates the moment the tires touch tarmac. Research teams in the United States, in Japan, and across Europe all took their shot at it and walked away with nothing. The waves were too delicate and the hardware needed to steer them properly did not exist. It was a wall built out of physics. And there was a second problem stacked on top of the first one. Every wireless system ever constructed handles signals using electronic circuits. Think of those circuits as roads through a city, with every signal being a car driving from one place to another. The catch is that different types of signal need entirely different roads. Low frequency needs one set of hardware, mid-frequency needs another. High frequency needs another again. A 5G tower is really just a stack of separate boxes bolted together, each one handling a single type of signal, each with its own amplifier, its own filter, its own antenna. It works, but it is expensive, complicated, and physically enormous. Now here is the breakthrough, and this is the part that has engineers around the world either thrilled or deeply uncomfortable depending on which passport they hold. A team working across Peking University and City University of Hong Kong worked out how to throw away all of those separate boxes and replace the whole stack with one single chip. And the trick behind it is beautiful. Instead of processing signals electronically, the way every wireless system in history has done it, their chip turns the incoming signal into light, processes it as light, then converts it back again. The reason that changes everything is that light does not care what the signal started life as. A beam of light will carry a low-frequency signal, a mid-frequency signal, a high-frequency signal, or a terahertz signal in exactly the same way. Instead of 10 different roads for 10 different types of car, you turn every car into light and send them all down one tunnel. That chip measures 11 millimeters long and less than 2 millimeters wide. It is smaller than the eraser on the end of a pencil, and it handles 9 separate frequency bands on one piece of silicon, which means 9 hardware modules currently filling up a tower cabinet collapse into something you could balance on your fingertip. What does that actually mean for you? If one tiny chip replaces an entire equipment rack, then building a wireless site becomes cheaper smaller, and dramatically faster. A rooftop installation that used to require a cupboard full of gear could run out of something the size of a shoebox. Multiply that across millions of sites, and this stops being a science story and becomes an economic story. And there is a layer underneath that. If a single chip can handle every band at once, including terahertz, then you no longer have to pick between reach and speed. There is that word again. You can build a system that uses slow waves for coverage and terahertz waves for raw speed at the same time, on the same hardware. The trade-off that governed every generation of wireless ever built stops being a trade-off at all. When the team published their results in the journal Nature in September of 2025, the chip hit 100 gigabits per second on a single channel. That is 2 full 4K films downloaded in 1 second. It switched between frequency bands in under 200 microseconds, which is less time than a hummingbird needs to flap its wings once. And that is only half the story. Remember terahertz? Here is where it comes back hard. A completely separate team at Purple Mountain Laboratories in Nanjing, working alongside China Mobile and Fudan University, took the exact frequencies everyone else had given up on and pushed a wireless signal through open air at 206.25 gigabits per second. Not a simulation, not a projection. A real measurement, independently confirmed and published openly. That is roughly 20 times faster than the 5G your phone is sitting on right now, achieved through ordinary air, using the frequencies the rest of the world had already declared useless. Now hold those two things side by side. One team built a chip that swallows an entire tower's worth of equipment into something the size of a fingernail. Another team proved the fastest frequencies in existence actually work outside a controlled lab. Both teams sit in the same country, and that country already has more wireless infrastructure buried in the ground than anyone else alive. The timeline matters too. The terahertz speed record was set in 2022, the chip landed in Nature in 2025, the Live City network switched on in 2026. Those are not scattered experiments happening by coincidence. That is a sequence, and the gaps between the steps are getting shorter. What happened next made it obvious this was never going to stay in a laboratory. On the 21st of April, 2026, China announced that its first pre-6G network had gone live in the city of Nanjing. Not in a test chamber, not behind a fence, but across a real city with 10 base stations carrying real traffic over real streets. Developers working on it reported speeds up to 10 times faster than current 5G in genuine outdoor conditions. The network was already running things that sound like they belong in another decade. Drone systems streaming live video with no perceptible delay. Factory robots taking wireless instructions as quickly as a physical cable could deliver them. Holographic calls where a three-dimensional image of a person is transmitted live. None of that is a promise about the future. It is running right now on a network you could walk underneath if you flew to Nanjing this week. Sitting behind that launch is $485 million of dedicated funding, written into China's national plan for 2026 through 2030, which places 6G alongside artificial intelligence and quantum computing as a top national priority. Nanjing has started calling itself the first 6G city on Earth, with Huawei, Qualcomm, China Mobile, and Ericsson all involved. And this is the point where everybody else started sprinting. South Korea, the country that got 5G running before anyone, committed $2.2 billion to its own 6G program and set a target of real pilot services by 2028. Samsung and LG both launched terahertz test programs of their own. There is that word again, showing up in somebody else's laboratory. Japan and the United States joined forces on a $4.5 billion initiative to develop 6G together, a partnership built almost entirely on the fear of being left behind. The European Union pushed over $100 million into 6G research spread across the continent. Add all of it together, and total global 6G spending as of early 2026 sat above $20 billion, with China, South Korea, and the United States accounting for roughly 3 out of every 4 of those dollars. When that many governments spend that kind of money that quickly, they are not gambling on a maybe. They are reacting to something they can already see. Nokia, one of the original giants of this industry, has publicly acknowledged that the center of wireless research is shifting eastwards. Ericsson projected in late 2025 that commercial 6G networks will begin going live around 2030, with China most likely arriving first. The international body that writes the technical rules every phone on the planet has to obey has already set a deadline of 2028 for 6G specifications. This race is not approaching. It is already running, and the runners did not start from the same line. Here is the part that matters more than any of the money. In the rooms where global wireless standards actually get decided, the rooms where countries argue over which technology every phone and every tower on Earth will be built around, China now holds roughly 40% of every 6G patent filed anywhere in the world. That is more than the United States, Japan, Europe, and South Korea put together. In plain language, when the rules of 6G get written, one country will have more influence over those rules than everyone else combined. And the country that writes the rules does not simply lead the technology. It decides who is allowed to use it and on what terms. This is not conference slides and press releases either. The Nanjing network has been operating since April of 2026 in a working city with real weather, real buildings, and a real interference. China's government confirmed it completed its first round of 6G technology trials between 2022 and 2024, producing more than 300 verified technologies. The second round is running now. The third round, covering pre-commercial equipment, begins in 2027. It is the same patient, step-by-step approach that built the world's largest 5G network in under 5 years. Now, I am not going to sit here and pretend there are no problems, because there are serious ones and they deserve honest attention. Terahertz signals still cannot pass through walls. They still struggle with humidity. Covering an entire city properly would mean transmitters on almost every building rather than every few blocks. And the electricity bill for running that many transmitters continuously is enormous. On top of that, Huawei has already been shut out of 5G networks in the United States, the United Kingdom, and Australia over security concerns. And those tensions are only going to sharpen as 6G becomes more valuable. Countries that adopt Chinese 6G equipment get the most advanced hardware available and become dependent on Chinese supply chains. Countries that refuse it risk falling behind. Sooner or later, every nation is going to have to choose. And there is one more problem nobody talks about enough. Building 6G requires people who understand wireless engineering, artificial intelligence, materials science, and advanced manufacturing all at once. China has openly admitted it does not have enough of those people. Neither does anybody else. 6G is not one field. It is a dozen fields stacked on top of each other. And the number of humans on Earth who can work confidently across all of them is very small. None of those problems erase what has already been demonstrated. They simply define how long the walk is from a working prototype to a network serving 1 billion people. Every previous generation of wireless faced that same walk and eventually finished it. Here is the bigger picture, and this is the part I want to leave sitting in your head. Every generation of wireless has quietly redistributed power. 2G handed it to Europe because the standard was European, and Nokia and Ericsson built the networks the world depended on. 3G moved it to America because American companies built the smartphones. 4G locked American dominance in place because the entire app economy grew out of Silicon Valley. 5G was supposed to continue that pattern. Instead, China put up more wireless towers in 3 years than the entire Western world combined, and the balance started shifting for the first time. With 6G, China is not just chasing the fastest network. It is going after the patents, the chips, and the standards simultaneously. If that works, the rules deciding how your phone behaves, what equipment your country's network runs on, and who collects a payment every time that technology is used get written in Beijing. And in 2027, the World Radio Communication Conference will allocate the spectrum above 100 gigahertz globally. That is exactly where terahertz lives. The countries that arrive at that table with working results will shape the rules. The countries that arrive with a slide deck will watch it happen. That is not a prediction. It is the direction the numbers already point. 40% of the world's 6G patents, 4.5 million 5G towers already in the ground as a foundation, a live pre-6G network running through a real city, and $500 million ring-fenced specifically to make 6G commercial. No other country on Earth currently has all four of those at the same time. The world that ran on 4G is not going to announce its own ending. It will simply start losing ground to something faster. Built by people who were willing to spend the money and take the risk, while everybody else was still debating whether to begin. That is happening right now. And this time, the center of gravity is not in Silicon Valley. It is in Nanjing, and it lives inside a chip the size of a fingernail that speaks every wireless language ever invented. If this video taught you something you did not know before, hit that like button and subscribe, and turn on notifications so you do not miss what we cover next. Now, here's what I want to hear from you. China built the largest 5G network on Earth in under 5 years and is already running a pre-6G city, while the United States and Europe are still arguing about how to divide up the spectrum. If the country that builds the network gets to write the rules, what happens to everyone who shows up late? Drop your answer in the comments below. We will see you in the next video.